Dear colleagues, this report focuses on the important problem of automating the software delivery processes and resource configuring in computing environments with parallel and distributed architectures to ensure the functioning of digital twins. To solve these problems, we propose a new framework. Within the process of analyzing and improving the efficiency of functioning infrastructure objects of environmentally friendly technologies, the direction of research related to the development and use of digital twins is actively evolving. As the digital twin of real object, we mean a virtual software entity that reflects important components in the object life cycle using physical data, virtual data, and information about the relation between them. For example, as a digital twin, we consider a model application for modeling and controlling the functioning of heat pumps of the Baikal Museum of the Irkutsk Scientific Center. The pumps provide heating to the building. The heat is released due to the decrease in the temperature of the input water from Lake Baikal by about 2 degrees. The use of heat pump decreases the consumption of electric energy and burn coal or gas. Thus, heat pumps significantly reduce soil and air pollution. Digital twin combines information about the object performance parameters, its detailed mathematical model, the variables of which are refined using real data and allow us to get the following benefits. Significant simplification of technical support of infrastructure objects represented by them, saving resources, minimization of the risk of possible errors and failures of equipment, extension of the period of stable and fault tolerance operation on these objects, getting the best possible return on investment and environmentally friendly technologies, and increase of the object competitiveness and improvement of the loyalty of their customers. The object model design, preparation and conduct of large-scale experiments are carried out using the Arlana Tools framework. It is designed to develop a special class of scalable scientific applications. The system of specification and modeling of the functioning process of infrastructure objects in the form of a digital twins belongs to this class presented on the slide. Designer construct a simulation model with Arlanda Tools. They use an object specification which describes object operation processes that can be interpreted and controlled. In the process of model execution, current monitoring data and retrospective data about object operations, processes and its environment are used. The current data is provided by the monitoring system, which receives them using peripheral equipment, controlling and measuring devices. Agents represent the controlling and measuring devices. Together with monitoring system agents, they support fog computing. Model instances are executed in parallel in an environment that integrates grid and cloud computing. The elementary functions of digital twins and agents are represented as microservices. Preparing a heterogeneous distributed computing environment on the resource available for performing modeling and carry out a computational experiment consists of the following main stages. Preparing and running virtual machines or containers, providing internet access and setting up a virtual private network, configuring a virtualized environment, delivering and updating components of a control system and executable models, monitoring, managing resources, lifecycle, and scaling. Each of the above listed steps can be viewed as a system administration task. A number of acceptable solutions are known for certain tasks. In particular, it's concerned with software configuration management tools of nodes in computing environment. Currently, software development is a complex and multi-step process. Usually, the process includes the steps of testing, debugging, and delivering software to end users. The development of an automated chain of effective delivery for both the applications in whole and their components and models is still a vital problem. In practice, a useful approach to solving this problem is the continuous integration of software. Configuration management tools automate the configuration process of various nodes and deploy a computing infrastructure with the subsequent delivery of application to its nodes. Developers are forced to accompany both the application and computing infrastructure or the software development environment necessary for debugging and testing during the continuous integration process. The general configuration management tool scheme is presented on the slide. Tools configure and prepare the nodes for work. Thus, the software developer defines the configuration requirements for the node. During the operation of nodes, their configurations are monitored and configured by the configuration management tools in accordance with the requirements. By executing special program code, scripts, the tools allow us to automatically lead the computing infrastructure to the target state. Such code is conventionally developed, modified, and maintained using version control systems such as Git. The software developer creates and stores the infrastructure specification in the repository. Then the translation component agent, independently or on the signal of the administrator, passes the specification to the slave nodes. In the nodes, these profiles are represented as a set of executable commands by deployment component or agent. We performed a comparative analysis of configuration management tools for computing infrastructures. The most popular tools are Puppet, Chief, Ansible, and SaltStack. Their general characteristics are presented in table. Also, system characteristics of configuration management tools presented on the slide. The monitoring of changes in configuration is an important characteristic in creating an experimental and production computing infrastructure. Push approach provides quick delivery of configuration to nodes. Only Puppet and Ansible support push. Both these systems have integration with Docker, Kubernetes, and Jenkins, which are actively used in the framework of continuous integration. In general, each of the systems has its own advantages and disadvantages. Based on the requirements for configuration management tools, we decided to integrate the Ansible system into the continuous integration chain of the Arvanda tools framework. This is due to the following reasons: support for managing the most popular operation systems, using an agentless approach that simplifies a system setup, using an imperative configuration of nodes, free distribution, using the push method, node control via the SSH protocol. The operation scheme of the proposed framework for designing and developing the DevOps processes is shown on the slide. As mentioned above, as a digital twin of infrastructure objects, we consider a modelable application for modeling and controlling the functioning of heat pumps of the Baikal Museum. Collecting, processing, and analyzing current and retrospective data is provided by a specialized monitoring system. Dependency resolution on certain versions of applied and system software libraries is an important step in ensuring the correct execution of a given application. To this end, it's needed to prepare each computational node participating in the computational process. We carry out the following operation: install system application and libraries, and place software agents, executable models, and input data. It's assumed that end users have access to various computational resources. Interaction with the framework is organized through the web interface. The inventory contains information about methods of accessing resources, for example the SSH protocol, passwords and encryption keys, and information about operating system, software and resource quotas. Resources can be heterogeneous. The problem of resource integration into a distributed computing system is solved using a virtual private network. In addition, the resource inventory includes various types of objects, such as devices and infrastructure objects. Each such resource hosts a software agent. Based on the task being solved, end users generate resource configuration profiles. Each task can be assigned its profile, which differs in the set of software and system environment settings. End users prepare executable models to be executed in distributed environment. Configuration management system automatically prepares the environment according to the profiles and list of resources for each task, and upon completion informs end users that it's ready to perform computations. Preparing the environment includes launching virtual machine and containers as needed. The monitoring system interrogates agents, collect performance parameters of all objects. Agents are united into a multi-agent platform based on the Java Agent Development Framework. On the slide represented a screenshot of the web portal of the temperature monitoring and visualization system. The following information is available to authorized end users: visualization of temperature, tabular representation of temperature, photos of the heat pumps with designation of installed sensors. Information are updated in real time in accordance with information from the database. The operator of the monitoring system can select any interval for visualization. Sensors are fixed on pipes of thermal devices. Data from sensors collected by the Raspberry Pi controller, which is placed in the heat pump control unit. We have organized an experimental environment to evaluate the framework prototype's effectiveness. Preparing the environment for functioning of the digital twin includes the following main stages. Stages 1 to 4 are performed manually by the end users using the framework web interface. We carry out a comparative analysis for performing stages 5 to 14 in the following two ways: manually and using the framework. Access to the nodes is carried out using a security key without a password via SSH. In stages 5 and 6, a specialized OpenStack add-in is preparing to execute the required number of virtual machines. Same way, containers are launched with Kubernetes in its add-on. Thus, stages 1 to 6 are performed at the same time in all cases. In the framework, stages 7 to 9 are performed by agents after their initialization. Some operations at this stage are carried out with the Ansible system help. Stages 10 to 14 are performed by agents. On the left figure, you can see the node configuration time in seconds for manual mode and framework use. Within the manual mode, some of stage 7 to 14 are semi-automated through applying the parallel SSH scripts. Nevertheless, we can see that setting up the environment in manual mode takes a few long time in comparison with the proposed framework use. The longest stages are 7 and 11 ones. They are related to installing system software and placing application modules. Right figure demonstrates the same operation for 10 nodes. In comparison with the manual mode, we see a decrease of the node configuration time by almost 4 times due to using the framework. Obviously, our approach demonstrates significant advantages over the manual mode at increasing the number of nodes. In this report, we applying DevOps methods to the digital twins for analyzing the operation of environmentally friendly equipment of infrastructure objects located in the Baikal Natural Territory. Currently, a large spectrum of the well-known tools for implementing DevOps practices exist. Nevertheless, the considered subject domain associated with systems that have distributed architecture actualizes new requirements that cannot be fully implemented by these tools. In this regard, we developed the prototype of the framework to automate such practices for improving the efficiency in developing and operating software for the aforementioned subject domain. The experimental results in applying the framework prototype have shown the possible improvement in performing the above processes in comparison with the manual mode. The study was supported by the following grants. Thank you for your attention. I am glad to answer your question.